Welcome back, everyone. Now that we understand classification performance metrics, let's head back to the notebook with logistic regression and see how we can produce these performance metrics with Python and scikit-learn. Alright, here I am at the notebook where we left off last time. As a quick reminder, we were able to create a logistic regression model and fit it to our scaled xtrain data and our ytrain label. And we can now take that model, that is log model, and either predict off of it for prediction of classes, or predict probabilities of belonging to each class, and then we can also explore the model's coefficients. So let's quickly start with the model's coefficients. And if we check out the model coefficients, it looks like we have negative 0.94 and then positive 3.4599. And recall that the features that it's being trained on, if we take a look at our data frame again, let's just check out the head of the data frame. The features were, the first one being age, and then physical score being the second one. And we can tell here just from the relationship to each other as far as magnitude, and from the sign, the relationship between the features and then the test result. And recall, the coefficients are in terms of belonging to the one class. Essentially, what this means is a couple of things. We notice that age is negative, which means as the age feature increases, we would expect the odds of belonging to the one class for the test result would decrease. And does that make sense to us? Yes, we already saw visually that as people got older, they tended not to pass the actual hearing test. And you'll notice for physical score, we have a value of 3.45. And that also makes sense because we can expect that as the physical score increases, the odds increase of passing the test result. Essentially, the likelihood increases of belonging to the one class for test result because the coefficient for the physical score is positive. And then based on the ratios with each other, it looks like physical score is a stronger predictor than age. And that also makes sense given what we saw with the box plot distributions. If you recall, and scroll back up to our previous plots, all the way back up to where we compared physical score to test result, look how much tighter the distribution is for physical score and how more meaningful the difference between distributions of 0 and 1 when it comes to physical score being. So clearly, high physical scores are a much stronger predictor than age. That is not to say that age is not a predictor. We did see it had a coefficient, but the ratios between them went from negative 0.9 and then physical score was 3.45. And so we can also do box plots for the age. For example, I can say y is now equal to age here to compare the same results. And you can see that these distributions are much closer together, although obviously there is a difference between them. Okay, so now that we understand the coefficients, both the reasons they're negative and positive, as well as the ratios of magnitudes between them, let's go ahead and move on to the classification performance metrics. For this, what we'll need to do is the following. We'll say from scikit-learn.metrics import, and there's going to be a couple of imports we can do here. The first one can be accuracy score, and this will just return back the straight accuracy percentage. We already know about the accuracy paradox, so we don't want to rely on accuracy alone. What I'm also going to include is the confusion matrix, as well as something called a classification report. So if you scroll over here all the way to the right, there is a classification report you can import. And I'm going to zoom out just one level so you can see everything that I'm importing. Accuracy score, confusion matrix, and classification report. And similarly to things like the mean squared error imports we did for metrics, what we're going to end up doing is passing in our predictions against the y-test data. So I'm going to run this. And now that I have my imports, let's start by figuring out the accuracy. Recall that I have y-test, which is the test classes, zeros and ones, and what I need to do is my predictions. So I'm going to say y-predictions, or y-pred, is equal to log model dot predict, and I'm going to say on scaled x test. Okay, so now if I take a look at my y predictions, they're also just zeros and ones. So let's go ahead and check out our accuracy. What I'll say here is accuracy score, shift tab, notice it takes the y true, which is our y test, and y predictions. So I'm going to say y test against y predictions, run that, and our test overall was 93% accurate, which means just given someone's age and physical score, 93% of the time, I can accurately guess, or essentially predict, whether or not they are going to pass the test result. Okay, so we already know there's an accuracy paradox. Let's move on to plotting things from the confusion matrix, such as precision and recall. So for the confusion matrix itself, what you can do is say confusion matrix, and then pass in y-test and y-prediction, and it will build out a confusion matrix for you, showing you the true positives and then true negatives, as well as the false positives and false negatives. However, there is a helpful plot function that will actually plot this out for you. And so we're going to import from scikit-learn.metrics, import plot confusion matrix. And so what's really nice about plot confusion matrix is for this particular function, you don't even actually need to do the predictions. You actually pass in the model, the scaled X feature test data, and then the Y test data, and it automatically creates the predictions for you and then visualizes the confusion matrix. Let's see how this works. We will say plot confusion matrix, and then I'm going to pass in my machine learning model. Obviously, you could swap out this model for some other model that is classification model. And then we'll say scaled X test and then Y test. So what's really nice about this plot confusion matrix is once you begin to learn about more classification models like random forest, you would be able to just swap in the model and then keep the same test data here. So when you run this, you should see a confusion matrix. However, notice now it's actually colored. And these are the same values we saw before. We can see 172, 21, etc. Except now it's showing you the true label and then the predicted label. And it also has a color bar gradient, so you can easily see the performance between them. Keep in mind, if your model's performing reasonably well, then the false positives and false negatives should be a very distinct color from your true positives and then true negatives. So keep that in mind that color bar is not super useful if your model's performing pretty well, because there's only actually 4 blocks to begin with in the confusion matrix. Now because of this, sometimes this color bar can be confusing, so there is actually the option to normalize these values. So if you do Shift-Tab on plot confusion, you'll notice it takes the estimator, the X feature values, and then the correct Y labels. You can scroll down here, and you'll notice one of the options here is normalize, which actually takes in the string true or pred, and essentially normalizes the confusion matrix over the true rows or over the predicted columns conditions, or you can do over the entire population. So if we do this, what we can essentially say is normalize equals to the string all. Run that, and you'll notice that everything starts to get normalized. And again, you can normalize this to the true values as well, or the predicted values. So you can see here, this sometimes helps with the color bar issue. It really depends on your model. Sometimes this is more confusing to people, so they rather just see the raw data itself, and then just keep in mind the total number of values that were passed in, doing something like length of y-test. Okay, so we know there's 500 values here, and we also just saw how we can display the raw confusion matrix values, or display the actual confusion matrix with a color bar, and then the labels of true label versus predicted label. We still haven't actually shown you yet precision and recall and F1 score. For that, we need the classification report. So recall we already imported classification report up here, and then what we're going to do here for the classification report is we'll say classification report, and you pass in your y true, so that is y test, and then your predicted values. And a really common beginner mistake is they just run classification report like this, print it out, and they see this weird output. That's because this actually is returning a string with new line calls, which means you have to actually print this out. So we print out the classification report, and then we see this nice formatted thing that looks like a table. Now that we actually have this table of the classification report, let's go ahead and describe it in a little more detail. You'll notice the classification report actually reports a precision, recall, and F1 score per class, which is quite nice. Essentially, these are now answering the questions of the class calls themselves. So recall here, if we take a look at one class, answers the question, how many of this class are you finding over the whole number of elements of this class? And the precision, for any value here per class, is answering the question, how many are correctly classified among that class? And then F1 score is the harmonic mean between precision and recall. And the support column is showing you how many specific instances you had of each class in this test set. You'll notice that it was relatively balanced. We had 193 instances of the 0 class in the test set and 307 instances of the 1 class. And in general, I would say if your precision and recall values for the classes are matching up quite closely to your overall accuracy, then you don't have an issue of an imbalanced data set. And accuracy is relatively easy to interpret, and as long as these values are not too far off for any particular class from your accuracy, then it's okay to start reporting accuracy and say you also had a balanced data set. You'll notice it also reports back the macro average and weighted average. Macro average is just going to be kind of your standard mean, and weighted average is going to weight that based off the number of instances per class. So that's also informative if you have an imbalanced class set. You'll notice since we have such a balanced class set, the macro average and weighted average tend to be almost the same here for most of these cases. Okay. Now you may be wondering, what if you just want the standard precision or standard recall? You can say from scikit-learn.metrics import, and there is a precision score, and there is also a recall score. So if you run those and check those out, precision score, it's going to take in your ytrue and ypred, just as we have up here. So let's take in ytest and ypred, and you can pass those in just as you wanted with accuracy score and get the overall precision, not per class, but just over everything. And that's going to follow the exact formula we showed in the theory lectures. And you can do the same thing for recall score, and then pass in ytest, ypred, and you'll see it's reporting 95%. These aren't going to be the exact same values as you see here, because in the classification report, it's showing precision and recall either per class or the averages between them. Here, we're actually following those formulas we showed directly from the confusion matrix here. Okay, so either way, we can see that overall, looks like we're getting around 93 to 95% precision or recall, and our accuracy is 93%, so there's no major issues on our model or on anything being imbalanced. The last thing we're going to explore in this lecture is how we can actually plot out the ROC curve and the precision recall curve. To do this, luckily, there are built-in functions. We're going to say from scikit-learn.metrics, and we're going to say import, and we can say import plot underscore, and there is plot confusion matrix, which we've already done, and there's plot precision recall curve, and then plot ROC curve. And this allows you, in one single simple function call, to actually plot and show these curves. So we can say plot ROC curve, and we pass in, just as before, the log model, the scaled test data, and then the y test. Whoops, accidentally cut that off. There we go. Scaled x test and y test. And this is going to create all the values necessary in order to create the ROC curve. And you'll notice here that there are parameters for you to edit this in Matplotlib. All you need to do is connect it to the axes that you're working with. So you can create a subplot figure above this, and then create that axes object and connect it to draw on that axes. So for example, we could say fig x is equal to plt dot subplots, and then we're going to go ahead and say here x is equal to x, run that, and now they're connected, which means I should be able to say here something like fig size is equal to, let's make this like 12 by 8, just to see the difference, and you can see here we're affecting it now. And then I can also increase the DPI if I wanted to kind of clear up this picture. Okay, so that's how you would connect your Matplotlib commands to this actual scikit-learn function, which is working off this axis connection. And that is the ROC curve, and there is also the precision recall curve, which is not as common as the ROC curve, but it is also useful. Essentially just measuring that trade-off between precision and recall. And to say that, essentially the exact same command, you can say plot precision recall, you pass in the model, log model, and then we're going to pass in our scaled x test data, comma, and then our y test data. Run that, and we can see the precision recall curve. And that's it. The very last thing I want to mention is recall, we already showed this in the previous lecture that we were working with this notebook, but we can also predict probabilities for a point, not just the class itself. So I can say log model predict probabilities as well as log probabilities, or probabilities probably easier to interpret. And then I can pass in something like my scaled x test data, run that, and I get back the actual probabilities. So if we grab, for instance, just the very first item here, I get these probabilities of belonging to the classes. So let's take a look at yTest at the very first location. So you notice yTest at 0, that correct class is 1. And so our model predicts that it has a 97% chance of belonging to class 1 and essentially a 2.3% chance of belonging to class 0. So that's how you're able to actually get the probabilities if you want to see them, instead of just the raw predictions themselves, which you get if you just call predict. You'll run this and it will choose the correct class or the predicted class. All right, that's it, and I'll see you at the next lecture.